All right. So last time I left you guys, I kind of went fast and heavy into the concept of finding the area underneath the curve, and it was conceptual, and I think a lot of people got confused, and that's okay because that's kind of what I expected. But I want to come back and I want you guys to think about area under the curve a little bit more slowly and a little bit more concisely today. Okay, so today in the problems that you're going to be doing, you're actually going to be calculating area under the curve using rectangles. Okay, we're using rectangles. We have no formula to find the area under the curve if the shape is a curve. Okay, if it was a circle, that would be one thing. But other than that, you don't have that many formulas in geometry that deal with anything other than straight lines. So let's say we've got a question that says approximate the area under the curve of f of x is equal to square root of x over the domain between 1 and 4, which means here's 1 and here's 4. And if this is the true area A, I want to find an approximation for that area A. Okay. And actually, in this case, I'm going to find two different approximations for the area because one of them is going to be an overestimate and one of them is going to be an underestimate. Now, since the only formulas that we know for areas involve straight lines, we're going to break this up into an area with a straight line. One actually kind of nice area that you could use to approximate this would be a trapezoid. If you look at this, it may not look like the trapezoid you're used to seeing because you're used to seeing what they call our isosceles trapezoids when the opposite ends are parallel and then these two sides are the same length. This still is a trapezoid. You still could calculate the area under that. You do know that it's an underestimate and it would be pretty accurate. However, this isn't the way that we're going to do it, and that's because we're that way isn't going to give you the intuition for the concept this is approaching in calculus. So we're looking at this range from 1 to 4, and our question tells us that we specifically want to use 6 rectangles. So I kind of want to think of this section right now between 1 and 4. Actually, I'm going to put the numbers on the top. And from 1 to 4 using 6 rectangles, well, if I did 2 rectangles, it would go from 1 to 3. Let's see, if I did okay, 1, 2, 3, that gives me 3 rectangles. I was wrong before. Okay, 6 rectangles is going to give me 1, 1.5, 2, 2.5, 3, 3.5, and 4. Okay, that's nice because everything stops at halfway. And another way I could have gotten there would be by taking the length of the whole interval, 4 minus 1, which is 3, and divide it by 6, which is 1/2, okay? Which essentially means that each of my rectangles are going to have a width of 1/2. And also I want to remember that notation is this is x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6. And that may be more than you need. The notation, don't let the notation throw you off. But so here is 1.5. Actually, I take that back. Here is 1.5. Here is 2.5. Here is 3.5. Okay. Here is f of 1. Here is f of 1.5. Here is f of 2. Here is f of 2.5. F of 3, f of 3.5, and f of 4. So the first time I'm going to do it using left endpoint rectangles, okay? So I'm making a rectangle from the left edge of this region between 1 and 1.5. And then from the left edge of the next region between 1.5 and 2. And from the left edge of the region between 2 and 2.5. And from the left edge of the region between 2.5 and 3. And from the left edge of the region between 3 and 3.5. And from the left edge of the region between 3.5 and 4. And if I think of what's that area represent, or what does that area equal? Well, each one of these shapes is a rectangle, and each one of them has a width of 1/2. So I could think of it as 1/2 times these 5 left endpoints. So it would be 1/2 times f of 1 plus 1/2 times f of 1.5 plus 1/2 times f of 2 dot dot dot, and the last one would be f of 3.5. It would have to be times 1.5. Or I could think of it as area equals, I could factor out the 1/2, and it would be f of x naught plus all the way to f of x sub 5. Or if I just wanted to throw in what I already know to be in there, I could think of this as area is equal to 1/2 times, well, the first rectangle is going to be a height of 1. The next rectangle is going to be square root of 1.5, because square root is a function, plus the square root of 2, plus the square root of 2.5, plus the square root of 3, plus the square root of 3.5. Whatever that answer is, let's see. Actually, let's do it on here, and I think I could do sum as n goes from 0 to 5 of square root of 1 plus n over 5. And that's my answer, approximately 7.3. And then if you think of what I also am going to ask you to do in a lot of these cases, because I know that I'm also going to ask you to do right endpoint. And what do I know about that approximation that I just got is that it's close, pretty close, but it's not exactly right. And also I know that the true area A is greater than 7.3. So what I might want is an overestimate. And how could I get an overestimate? Well, I'm glad you asked. I could, instead of taking the left endpoint from each spot, I could take the right endpoint. Okay, so now the right endpoint between 1 and 1.5 is above the function. If I think of the right endpoint between 1.5 and 2, that's above the function. If I think of the right endpoint between 2.5 and 2, that's above the function. If I think of the right endpoint between 2.5 and 3, it's above the function. If I think of the right endpoint between 3.5 and 3, that's above the function. If I think of the right endpoint between 3.5 and 4, that's also above the function. And now notice I still have 1, 2, 3, 4, 5, 6 rectangles. I have one rectangle that's completely new. And if I think of, you can, so these rectangles from the last one, you can still see what the top of them, because the black line is on the top of them. You could think of these as 0, 1, 2, 3, 4, 5 from the black ones. And what I want you to be able to see is that there's a lot of overlap here. Okay, this orange rectangle, sorry, this the first orange rectangle right here is equal to the second black rectangle, okay? The second orange rectangle is equal to the third black rectangle. So these formulas have a lot of things in common. What happened with the black was we had 0, but we didn't have a 6. And what happens with the orange, the new one that I'm doing, is we have a 6, but we don't have 0. And if you think of what that means on the scale that we developed before, I'm evaluating the function at x sub 1, x sub 2, x sub, up to x sub 6, but not at x sub 0. And so now the area is going to be, I'm not going to write it in all these different ways. I'm just going to think of it in one way, which is area is equal to 1/2 times the height of the first rectangle, which is 1.5, plus the height of the second rectangle, which is 2, plus and if I think of how I have to change that approximation from the one that I did before, well, a lot of the stuff is going to be the same. It's going to be the sum, and it's still going to be the square root of 1, because that's the left edge, plus, oh, I think I messed up before. This should be n over 2. That should be n over 2. So my true answer from before should have been 8.82. I'm tripping. And then now I'm going to have the same formula here, except that I don't want to start at 0, right? I don't want to start with the 0x. I want to start at 1. I want to start at 1, and I want to go up to 6. And now I have 9.82. That's pretty cool. So it's a difference of 1. And you could probably think of a reason why that is. Well, you can think of the 6th rectangle is f of 4, which is the square root of 4, which is 2. And the 0th rectangle, which is f of 1, which is 1. So there's a difference of 1 between the 0th and the 6th rectangle. But also, if you just kind of sit with these two different expressions here and think of what would they do. Well, this one would go from 0 up to 5. So the first thing I'd plug in 0 for 0. So I'd get the square root of 1. And then the last number I'd plug in is 5. So I'd get the square root of 1 plus 2.5, which is the square root of 3.5, which is what I had as my last rectangle here. And the other one would start at 1. So I'd have 1 plus 1 over 2, which is 1.5, square root of 1.5. And the last rectangle I do would be 6 over 2, which is 3. So 1 plus 3 is 4, square root of 4, which is that. So those summation notations are how I would approximate those areas. And now I have a better approximation for that true area. And in calculus, you'll learn a perfect way of approximating it. But you should still be able to answer this. Let's say I wanted to get more accurate. What's one thing that I could do to get more accurate? And I'll admit there are several right answers for this, only one of which is the one that I'm looking for. But if I wanted to, I could divide this up into more rectangles. Okay, so if I changed this number 6 to, let's say, 12, then the approximation I'm going to get is going to become more accurate. And it allows me to like get way, way, way more rectangles and make you do way, way, way more tedious calculations, which is one of the joys of teaching math. But for now, I'm not going to have you guys do that. Today's problem, one of the problems in the book has you look at this function, f of x is equal to 9 minus x squared. It goes between 1 and 3. It's going to have you calculate the area. Keep in mind that there's a difference between these. There's a lot of differences between these two functions. One of them is this function is increasing and this function is decreasing. And so when you have a function that's decreasing, it changes some of the assumptions that we made based on what's an over and an underestimate from the increasing function. And I'll let you explore with that a little bit, but hopefully this was somewhat helpful.